So our next speaker is very relevant for our workshop. It's Kevin Buzzard, who is currently Professor of Pure Mathematics at Imperial College London. And Kevin was one of the contributors to the issue of the Bulletin of IMS I mentioned earlier. And he has delivered many interesting lectures on AI and mathematics. I have seen several of them. He's currently focused on formalizing Fermat's last theorem, and his talk is titled Formalizing Fermat.
Thank you very much. Can you hear me?
Yes.
Yeah.
Great. Thank you very much for the invitation to this conference, and thanks to all of you for showing up. What's this about? So let me start with an introduction. This is what motivates me. In the 1800s, humanity had generated a lot of music, and the way music was stored was that you would write down the notes, and you would write down, which instrument to play the notes with, and how hard to play the notes, and how fast to play the notes. And we had some language to express all this. And then, of course, by the 1980s, things move on. And by the time I was a student, essentially all music was now recorded on vinyl, which is a much more convenient way to store music, right? Because now you can actually listen to it in your own home rather than just having to listen to it in your head. But then in the 1980s, something weird happened. There was this thing called the CD. Music was digitized. And at the time, I don't have any evidence that people knew what was going to happen. People just thought it might be a good idea to digitize music. So music got digitized, and the start was around the end of the 1980s. And now music is all in all music is in my pocket. And that's a really so by the 1980s, 300 vinyl albums were filling up my student room. But now I have the world's music in my pocket. And so digitization really turned the world of music upside down. It changed the way people consumed music. It changed the way artists worked with their audience. But digitization turned music on its head. And I think that one of the things humanity should be very proud of is the fact that it's generated so much beautiful music in the last 2,000 years. So that's sort of a really, really large body of work, of your beautiful human-generated work. And all of that work has now been digitized. And so, of course, where I'm going is also over the last 2,000 years, humanity has produced a huge amount of amazing and interesting and deep and profound and beautiful pure mathematics. And I think we could also argue that humanity should be proud of what it's done here. We've done amazing things. We found statements which are very simple to explain and extremely deep and profound to prove. And we've discovered this beautiful thing, mathematics, and we're writing it down in LaTeX. And as far as I'm concerned, that's not digitizing it, right? LaTeX doesn't count. Sort of LaTeX is like vinyl. It's sort of much better than, LaTeX and PDF are a much better choice than sort of physical paper that we were doing in the 1800s. It's definitely a step in the right direction, but it's not, it's still human words are involved and human expressions, and it's very difficult. Of course, AI experts are attempting to get their systems to read and understand archive, but somehow the fact that it's still at the end of the day, it's still written in human language. So digitizing things, it changes these things. It gives you a new way to work with these things, and it can be seriously disruptive. And we have the bonus that along the way, when you digitize mathematics, you get it into the form that a theorem prover can understand, an interactive theorem prover, as Sergey pointed out this morning. digitizing mathematics. We regard the LaTeX literature, nowadays we call it informal literature, and turning it into formal has the advantage that we check our arguments along the way. So that's one of the many bonuses. But let me remind you, there's a vast amount of music, and they digitized all the music, right? And it turned music on its head. And so, of course, the question is, how are we going to digitize all the mathematics? And then, if we do that, then how are we going to use AI to turn the mathematical world on its head? How do we disrupt mathematics? That's for me the really appealing idea. Even though I'm not an expert in AI at all, but I would like to turn my subject on its head. I think that's a very worthy goal. And so, of course, the first question, AI disruption, I'm not an expert in, but I am knowledgeable about the first step in this disruptive plan, which is, have we even got tools which are capable of understanding all known pure mathematics? So that's a much simpler question than how do we use AI to disrupt mathematics. So for this simpler question, I have a conjecture that I'm quite confident about. So that should say known, sorry, not KNWN. I've spelt known wrong. All the correct parts of known mainstream pure mathematics. I claim, do you know what, I'm going to fix it because, oh no, I'm not going to fix it. Why not? All the correct parts of known mainstream pure mathematics, I claim that they can be formalized, given the kind of tools that we have now, given modern interactive theorem provers. And I don't think that was true 10 years ago. 10 years ago, we certainly had some amazing data points. We had a full formalization of things like the four-color theorem and the odd order theorem. But these are very specialized statements. And mathematics is somehow much broader than the kind of topics which are covered by those big formalizations. So why do I believe this conjecture? Well, I think I have a plan to give a strong evidence for this conjecture. And the idea is, of course, that I'm going to attempt to formalize or lead a team which is going to formalize a proof of Fermat's last theorem. Oh, I've found that thing. Look at this. I reckon I can fix it. If I do this, let's see what happens. There we go. The known is now spelled correctly. So I'm going to attempt to prove this conjecture by showing that the tools we have are capable of understanding a proof of Fermat's last theorem. And why Fermat's last theorem? Why not some other random conjecture in my area? And the reason is that Fermat's last theorem, the statement is an arithmetic statement, but all known proofs use a vast amount of 20th century mathematics. So, for example, there's a lot of analysis involved, in particular harmonic analysis, through the work of Langlands, and then through topology to differential geometry and algebraic geometry. There's representation theory involved via the Langlands program. There's arithmetic geometry. We don't just need algebraic geometry over fields. We need Grothendieck's version of algebraic geometry. And then, of course, there's cohomology and the standard machinery coming from category theory. There's algebra. And there's arithmetic, and not just basic arithmetic, really non-trivial statements like class field theory, which was somehow one of the highlights of 19th century mathematics. So all known proofs of Fermat's last theorem. I'm excluding the announced proof by Mochizuki et al. Because that proof is not accepted by the community, and that would use fewer of these tools, is my understanding of it. But it's not accepted by the community. The sort of the Taylor-Wiles approach uses all this machinery. So I kind of feel that if we could formalize a proof of Fermat's last theorem, this is a huge amount of evidence. This is nothing to do with AI, right? This is a different question. This is, can interactive theorem provers, are they now at the stage where they can understand everything that we're doing? And I think that if we can do Fermat, then, quotes, we can do anything. Of course, that's not a proof because you can point you know, to areas of mathematics like low-dimensional topology or sort of infinity category theory. You can point to areas of mathematics that aren't really used in the proof, but somehow at least this is evidence that if we can do Fermat, we can do anything. So let me just say a bit, what is this project? So the idea is I got a grant that buys out my teaching for 5 years, and in return, I'm just going to devote a lot of my time every week for the next 5 years into actually making this a reality. And I should say that my proposal was not to formalize Fermat's last theorem. That's sort of what gets reported in the sort of the mainstream press. But what I actually said I would do in this grant, I said I would formalize the sort of the key new innovation that Wiles introduced, the modularity lifting theorem, sometimes known as an R equals T theorem. So that's all that I claim to do. I didn't say I would formalize a full proof of Fermat. I said I would formalize an R equals T theorem. And the ideas where that happens are in the original Wiles and Taylor-Wiles papers. This is from the early 90s. So this maybe is a total of 150 pages of mathematics. And so, of course, once we have the key new insight from Wiles and Taylor-Wiles, of course, it's going to be easy to prove Fermat's last theorem, right? Because that was the big blocker, this modularity lifting theorem. And then, of course, it's all downhill from here. And, of course, that was how we felt in the 1990s, that, you know, they'd had the key new idea and then it was easy. But, of course, in practice, this is not the end of the story, because we need to get a proof of Fermat's last theorem from the axioms of mathematics. You know, that's how these theorem provers work. So if all goes well, in 5 years' time, I will have achieved what I said I would do, and I will have reduced the proof of Fermat's last theorem to results which was completely standard by the end of the 1980s. That's the idea. And so here are examples of results which were completely standard in the 1980s when Wiles announced his proof. Maser had proved 10 years prior to this that he'd realized that every elliptic curve over the rationals can have at most 16 torsion points. And the proof of that is 150 pages. Langlands had proved very profound results for inner forms of GL2. We only need cyclic base change for GL2, but this is a very delicate analysis of the trace formula, in particular in the non-compact case. And there's also another book by Jacquet and Langlands where they managed to transfer. This is all about, if you've got an automorphic form for one group, how do you make an automorphic form for another group? That's the basic question. And an automorphic form, you know, is a definition in harmonic analysis. And so this is a question. These are very delicate questions in harmonic analysis, which are resolved by these techniques using the trace formula. So this is hard analysis. And then we also need some hard arithmetic. We need to attach Galois representations to certain automorphic forms. And you usually do this by finding them in the cohomology of Shimura varieties. So that, again, that's a lot more machinery coming from arithmetic and algebraic geometry. And then we need all the background that makes, you know, these are research level results. And then we need all the background that make these results feasible. So huge chunks of Grothendieck's work from the 60s, you know, all the sort of basic foundations in analysis and representation thing. So this stuff is piling up, right? I'm just saying in 5 years' time, I can do 150 research level pages, but then there's 1,000 more research level pages and 1,000 more, you know, pages of background. So formalizing a full proof of Fermat's last theorem is a gigantic problem, right? And humans could go about starting this problem. Indeed, that's what's going to happen. Humans can go about starting it. But when you look at how big the problem is, it's very natural to ask, are there going to be tools that we have now or that can be developed that can help us do this job? Because doing it right now, when you let me perhaps stress for people that don't realize, when you're formalizing mathematics, this is a manual process, right? You type in proofs into the system manually. You don't have to work from the axioms of mathematics. You can use tactics, which are sort of higher order techniques. but it's still very slow going. I mean, Sergey mentioned this morning that Howard suggested it's sort of 7 times slower. I've heard him say 10 times slower. Writing in LaTeX is one thing. Writing in Lean is perhaps 10 times slower. So it's a very slow process, and there's a lot of pages. So that's sort of the introduction. And now let me talk about how this relates to AI. And to be quite honest, it's clear what the AI community can do for me. They need to give me a machine where I just feed in 300 pages of LaTeX and out comes 300 pages of Lean, right? And this is a translation problem. Okay, and computers are getting really good at translation problems, right? We can give a computer a bunch of English and we can output a bunch of Chinese or a bunch of French or a bunch of Hebrews. There's a lot of this stuff available on the internet, so the systems can train, and as a result, these systems have now got very, very good. And so what I'm suggesting is if the systems can solve this translation problem, then that's great. Then we're done. Right? The whole process will be very easy. But the problem is there's a huge amount of language available on the internet to train on. And right now, the amount of Lean that's available to train on is very small. And so training the systems to write perfect Lean is currently science fiction, unfortunately. It sort of sounds like it might be a viable problem, but because the amount of Lean available to train on is too small. So right now, this translation problem sounds like it could be feasible, currently isn't really feasible. Also, writing perfect Lean is an extremely difficult task. I should say, here's what sounds like a much easier translation problem. Why don't we take 1 million lines of Lean 3 code as input, and the output needs to be 1 million lines of perfect Lean 4 code. And even that was extremely difficult to do, even though Lean 3 and Lean 4 are extremely similar programming languages. That took the community, years of work, 8 months of very solid manual work, plus sort of a year of developing the tools, which would make that process not completely tedious and impossible. So this translation process is much harder than you might naively think. But of course, progress is happening and things are moving very, very quickly. So in 5 years' time, when I've manually translated 150 pages of Wilder's work, me and my co-workers, will it still be science fiction? Will people have managed to develop tools that generate gigabytes of synthetic Lean code? Computer written Lean code, which then another system could try and train on. That sounds completely wacky, but actually it's not completely out of the question that will be the way this problem is solved. So we don't really know what will happen in 5 years because the area is currently a long way from being able to solve this, but it's moving very, very quickly. And so it's sort of difficult to guess. We have something which is far away, but moving very, very fast, sort of vaguely towards us. And the question is, will it hit us? Right, and that's sort of very difficult to work out because it's too far away to do the calculations. So experts have different opinions about what's going to happen here. And I'm not going to offer an opinion. My opinion is I don't know. So let me say a little bit about what formalization of mathematics actually looks like in 2024. And one breakthrough that we have had in the last few years is that Patrick Massot's Blueprint software has given us a framework, and also the Lean and its maths library together have given us a framework where we can actually formalize non-trivial known mathematics in sort of real time. And the two famous examples that people always mention, it's terrible, really. These are the examples that people mention because Fields medalists were involved. But there are many other examples, for example, like the sphere reversion project and the current work on Carlson's theorem in harmonic analysis, which are not sort of Fields medal worthy, but there's still many more data. So we have many more data points than these 2 data points. But to give examples of some data points we have, there's 2019 work of Clausen and Scholzer, which he suggested would be a good experiment for a formalization project. And this was done in a year and a half. And then 4 years later, we have 2023 theorem of Gowers, Tao, Green and Manners. Gowers and Tao, both Fields medalists. They resolved this non-trivial conjecture in additive combinatorics. It was a 33-page paper, and the entire thing was formalized from start to finish. This plus references in a 3-week period, right? So 30 pages of additive combinatorics was done by a team of 25 people in 3 weeks. And this was modern mainstream mathematics being formalized in real time. So let me show you what that sort of system looks like. And let me show you, not with regards to those works, but with regards to this Fermat's last theorem project. So everything in this game is free and open source. You know, when it comes to AI, that's less often the case. There's private AI stuff, but this mathematics stuff is all free and open source. Here's my blueprint. And in particular, the interesting thing to look at is the dependency graph, which looks like this. This is the area of the dependency graph I'm working on right now. We're proving a theorem in Bourbaki, a technical result in Bourbaki, which we need to define Frobenius elements. And there's my little graph that's sort of working on this. And this is another project which is sort of halfway completed. And then this is sort of another project there, about an Adelic project. Green means it's done, blue means it's ready to be done. And here's another project, here there's the conclusion of Fermat's last theorem here. And you can click on all of these nodes, and you click on these nodes, and you can see a statement in LaTeX. I mean, let me click on this, here's there's an easier thing, which is already done. There are no solutions in positive integers to a cubed plus b cubed is c cubed. And here's another solution. If there's a counterexample to Fermat, then you can reduce the case to p as an odd prime. And you can you see there's options here. There's LaTeX and lean. So we have these. These are very beginning proofs at the beginning of the proof of Fermat's last theorem. You can click on the LaTeX and you can see. We have LaTeX here, right? This is human. This is not lean code. This is human readable code. This is code just written in LaTeX. That you can read. And let me go to an area. This has all been done. Let me go to a region that's not being done, that's being currently worked on. We need definition of Frobenius elements, and we're going to do that via sort of a deep theorem in Bourbaki that we're in the process of formalizing. Here's this theorem here. And so, as I say, this is LaTeX, which humans can read, and they read it, and they see this. Let's find a theorem. There you go. There's a theorem. They see there's we have some definitions, and we have this theorem here, and you can look at this. You can look at this theorem in lean. We can jump to the lean. There's the documentation, and we can jump to the lean code, and we can see that this lean code here, it has a sorry in, so that the statement of the theorem has been formalized, but the proof has not been formalized. Okay. So we need this proof to prove Fermat's last theorem. This is one of many millions of theorems we need. And we can scroll down here. Yeah, here's many more theorems that are not, some theorems are done and some theorems are not done. You see, there's a proof that's been done, and here's some more proofs that have not been done. And what the idea is for a human to contribute, the human goes to, let me go back. The human goes to the LaTeX blueprint, and the human reads the proof. And in this case, there's a one-line proof. And now this has to be translated into like 10 lines of lean. But you see, to do that small task there, you don't have to understand a proof of Fermat's last theorem. This is the beauty of the system, right? The people that will work with me, they don't all have to know a full proof of Fermat's last theorem. They just have to be a graduate student in number theory that knows, or maybe even an undergraduate who's capable of reading some basic ring theory and group theory, and is also knows the lean language and is capable of formalizing that thing. You see, this definition has a tick, which means it's done. This lemma does not have a tick, so this lemma needs to be done. But doing that, this is a sort of a 1-hour project or maybe a 10-minute project that anybody that knows something about lean can do. So the idea is we break up the proof of Fermat's last theorem into tens of thousands of very small projects, and then humans collaborate and solve those projects. And this graph I showed you, and where's the graph gone? Let me get the graph again. There's the graph. And this graph will slowly go greener and greener and greener. And when it goes, when it's all gone green, then we prove Fermat's last theorem. So that's what it looks like, the process of formalizing. So what do we have? Right now we have GitHub Copilot, and that's the tool that works. If I type in lean into my IDE, it sometimes guesses the LaTeX. I'm typing in lean and LaTeX, right? This is what the blueprint is. It's lean and LaTeX. You type in the lean, it guesses the LaTeX. You type in the LaTeX, it guesses the lean. I said already that this was an unsolved problem, but I was talking about doing 300 pages at once. When you're doing it lemma by lemma, sometimes the system works very well. And sometimes it works very badly. And sometimes, this is the worst thing, sometimes it looks like it's worked very well, but it's made a mistake. Right? It's made a mistake in a definition. And in fact, then you kind of think, oh, that looks right. Let's just click tab. And there we've got our new definition. And the definition's very slightly wrong. And you try use the definition later on, and it doesn't work. And you realize you've made a mistake. Or the theorem is stated slightly incorrectly. And this really happens. This happened to me earlier this week. So right now, what am I using to do this task? I'm using GitHub Copilot plugged into my Visual Studio Code. And this is a large language model that's trained on everything. So it's not specifically trained to do translation between lean and LaTeX, but it's doing it very well. And you can think, well, maybe we could beat GitHub Copilot by taking a small model which has specifically been trained on lean and on LaTeX, and his job is specifically to do that. But unfortunately, the smaller models just don't work as well, even if they're more specialized. Right now, the larger models that are trained to do everything seem to work better than the smaller models. So that's just an observation. The big problem we face, really, the reason that the whole process is far more tedious than you would like, is that in the mathematics textbooks, they say, now this is obvious, and this is obvious, and this is obvious. And ideally, lean should agree, right? This is one of the many reasons why translation is not easy. How do you translate the line, this is obvious? Because no details are given, because the idea is the human is supposed to be able to see how this works. So right now, this is problematic. Because the moment, of course, a mathematician understands an argument, they say it's obvious, right? This is one problem. So you see this is obvious in the literature, and it might not be obvious at all. It might just be obvious if you've paid very careful attention to what's just been happening. And then the other problem is there are things which really are obvious. And it's not just because you're a smart mathematician that they're obvious. There are things that really are obvious, but unfortunately, they're still a long way from the axioms. Here's an example. X add y cubed is x cubed add 3x squared, y add 3x, y squared add y cubed. Right? That's obvious. But if you actually try and prove it from the axioms, you expand out the brackets, and then you kind of imagine it's all easy, and you've just got to clear it up and and group every term together. That's not at all true, because all the brackets are in the wrong place. You've got 8 terms all added together, but to actually rearrange the terms to put all the x squared y terms together, that's a non-trivial combinatorial problem. If you only have associativity and commutativity, which are the axioms for a ring, then to rearrange terms is you've got to find some crazy permutation of S8. It's worse than S8. It's S8 with random brackets in, and you can only do certain transpositions. So proving this statement is a really hard combinatorial problem if you're only allowed to use associativity and commutativity. But of course, you just write a tactic that does it for you. So this was done in 2018. And another example is the degree of a polynomial. So we automated degree of a polynomial in 20. The degree of that polynomial is obviously 3, but the mathematical proof of that, the formal proof, is slightly messy. But now we have a tactic that does it. So the other big area where we're missing something is sledgehammer. We need a machine that does obvious things. And in Isabelle Hall, which uses a higher order logic and not dependent type theory, this uses a simpler logic. And that means that certain parts of modern mathematics are very difficult to do in this system, but it also means that if you want to leverage other systems, automatic theorem provers that typically work in first order logic, it's much easier to link those automatic theorem provers to Isabelle. And that's what the sledgehammer tool does. It solves a lot of obvious goals by farming them out to powerful automated theorem provers and then translating their results back into Isabelle. And this is much harder to do in a more profound logic like Lean's logic. So you've got to, do you want to do category theory and homological algebra? Yes, we do. Then we can't use Isabelle Hall, really. It will be too inconvenient. And so now we've got the problem that we can't use sledgehammers. So another issue, I've got to wrap up. Another issue is missing definitions. So what was the big breakthrough with Fermat? Fermat followed from the semi-stable Shimura-Taniyama conjecture. That was a theorem from the 80s. So why don't we just state the semi-stable Shimura-Taniyama conjecture and ask the AI to prove that? And the problem is we can't state the conjecture right now in these systems because we don't have the right definitions, the definition of what it means for an elliptic curve to be modular, for example. And formalizing definitions is, you have to be careful, right? Formalizing theorems, you just get the theorem, you get the compute, you state the theorem, you get the computer to prove it. You don't need to check the proof because this, lean is checking the proof, but definitions you have to check very carefully. So more and more definitions are going to be formalized, and then we'll use the definitions, we'll check that they work. But this needs to be done, right? So within a year or two, I'm hoping we'll have a lot of modern definitions from number theory. So we'll be able to state the hard relevant results, which I'm going to be assuming, like Langland's cyclic base change theorem. So within a few years, we'll have a really nice challenge, right? To prove Fermat's last theorem, to prove one simple looking theorem, you just have to prove 10 complicated looking theorems. And my claim is that this is progress. But, unfortunately, I don't believe in magic. So I don't really know how far things will go. But here's the challenge which might be accessible. I showed you those tools. We're going to develop a lot of LaTeX proof of short LaTeX proofs of lean statements. And we're going to be manually translating those LaTeX proofs into lean. But just for very short LaTeX proofs, is AI going to help us with that? And I think that's definitely a viable thing. That's what I'm hoping will be the next step, is that I will write down a bunch of LaTeX theorems and proofs and lean statements and say we're going this way, and AI will start filling in lean proofs of short LaTeX. They will start translating short LaTeX proof into lean. So this is the last slide. Formalizing mathematics is out of reach right now, but it's sort of theoretically possible, but in practice it takes too much time. AI doing it autonomously is a dream, but just proving Fermat is asking for something much simpler. Even just doing Fermat is going to take a long time, and AI doesn't help very much, but AI is moving very, very fast. So maybe by the time I'm wrapping up that project, maybe AI will help more, and then it will be clearer which direction we should be going next. But currently it's very difficult to predict where we'll be when I've done the modularity lifting theorem, which I'm optimistic I'll be able to do. And part of the reason is it's difficult to know what's going on. So that's it. Thank you very much for your attention. If I should thank you in particular, I should thank Elena for asking me to give this talk, because it made me sort of try and work out, what the pertinent questions were, which was not something I'd really thought about until this point. So thank you very much indeed for this opportunity.
Thank you. Do you have questions? One up. Maybe David. Maybe will you ask orally? David.
Yeah. So I guess the two parts of my question are you familiar with David Dalrymple's ARIA project on guaranteed safe AI, and specifically the part that's looking at proof systems? And then the second part of the question is how much, because lean is a formal system, presumably it's much easier to generate valid steps in lean and validate those. And then presumably you can use that to generate statements in a LaTeX format of the statement and use that as training data, rather than trying to rely on all of the kind of human translated data. And I'm wondering if that's something that you've looked into or something that you're optimistic about. You're muted. Sorry.
Thank you. My understanding is that the reason language models can write Python code so well is there's 1 billion lines of Python code on the internet. And the problem is there's only 1 million lines of lean code on the internet, maybe 2 million by now. And this is orders of magnitude too small. So getting anything to learn lean seems to be a difficult problem. You either want one of these big tech companies to concentrate specifically on lean and give a publicly available tool, which maybe is unlikely, or you want small independent groups to make smaller models that do useful things. And right now that hasn't happened. So it's clearly something. There's clearly something we can think about, right? Just this translate. It's clearly a viable kind of project, but we don't have enough data. So right now I've seen nothing useful. But lean to LaTeX and LaTeX to lean, that's a weird question. I give you the weird answer. I write my LaTeX first, and then I translate it into lean, and I've seen Copilot be useful. But that's my workflow. I write the LaTeX, then the lean. Whereas I was talking to Terry Tao recently, has been writing the lean, then the LaTeX, and he said that it was also useful for that. And so it seems to be useful for both, but I've only been trying to do one way. Because the point is, how do I fit into this picture? I know the proof of Fermat's last theorem. I was a student of Taylor. Me and Taylor have developed a strategy for getting there. I'm somehow, and that's the thing that a lot of other people don't know. So it's my job really to write the LaTeX. So that's why I've only been doing LaTeX to lean translation.
Thank you. I would point you to David Dalrymple's ARIA project, which has
thank you for the link.
60 million pounds to spend over the next couple of years on trying to figure out how to formalize mathematics for safe AI.
Okay, I was completely unaware of this work.
And is very excited about Lean 4.
Yeah, I'm speaking at an AI conference, but I'm really not an AI expert. I try and keep up with what's going on, but that's about it.
Oh, yes.
You mentioned that logic of Isabelle is weaker than Lean. Does that mean that you can import Isabelle proofs into Lean?
No.
Oh,
it's very difficult doing anything like we couldn't even import Lean 3 proofs into Lean 4. That was a phenomenally difficult task. And moving from a system, even translating between Coq and Lean would be very difficult, or ROC as it's called now. And they both have the same foundations, dependent type theory. So Isabelle to Lean is going to be even harder because the logic is different.
Can you add some axioms and then?
Yeah, you could try. Another problem is that when you get let me give you a data point that really happened. A very impressive result. Mario Carnero wrote a system which translated MetaMath's proof of the prime number theorem into Lean. And so MetaMath is a system based on set theory. So this is kind of completely incredible. We've gone from set theory to dependent type theory, and it worked. You pressed the button and it worked. And we had sort of just gigantic 30 megabyte incomprehensible, impossible to read statement. And the conclusion of the statement was that Isabelle's prime numbers grew like x over log x, where x was an Isabelle real and log was Isabelle real's log. And what we wanted was that Lean's prime numbers grew like Lean's x over log x with Lean's real numbers and Lean's log. So then, even after the translation, it's not done yet because you have to prove that Isabelle's definition of log and real's definition of, like Isabelle's real numbers and Lean's real numbers satisfy they're both complete ordered fields. So by a theorem, they're uniquely isomorphic. And now you've got to prove that isomorphism matches Isabelle's log with Lean's log function. So even if the translation is done, it's sort of not perfect because there's still more work to do at the end of it. I mean, hopefully this might be easier, but there's all sorts of problems.
How do you kind of debug the core of Lean? So
how do I do what? So debug
the core of Lean. So why is it bug free?
Oh, that doesn't matter. Even if Lean is buggy, once you have a proof in Lean, it outputs the proof, right? When you compile the proof, it outputs the proof.
Yeah, so proof checker.
You have the directed acyclic graph that may, and now you can take that directed acyclic graph and just feed it into a type checker. right? It's like factoring. How do you factor a 200-digit number? Oh, that's really hard. Okay, let's write a gigantic computer algebra system that factors 200-digit numbers. Well, that computer algebra system might be buggy. Now let's give it a 200-digit number. Oh, look, it's produced two 100-digit prime numbers whose product is that number. Well, the system might be buggy, so the factorization might be wrong, right? But how do we check the factorization? That's easy. You just type in the product, you write an algorithm which multiplies 100-digit numbers together and it checks it's the 200-digit number. Right? Once you actually have the proof, who cares if the system's buggy? You just check the proof on a much simpler system. So you just use a type checker.
Thank you.
Thank you.